is the video that I wanted you guys to watch. It's going to take like 4 minutes, so just go watch on your own. Basically, it mentions this little town called Königsberg, which is now Kaliningrad or something like that. Anyway, that's an interesting part. Okay. Now, today's material is going to weigh a little bit more in the final, because it's not something that I expect any of you will be doing for the project. Okay, whereas other techniques that we taught in class is going to appear, I think, in your project. So I can break it there. This material today, which is about modeling graph data, is something that I'm going to test your knowledge on, I think, at the same time. So anyway, okay, let's begin. So today we are going to talk about graph data. Okay, graph data. Now, first of all, I want you guys to start your notebook, and I type in this command. You can just repeat it, just copy paste it, so you can have the same material to work with. Okay, so let's start with you have to keep pointing this thing, right? Let's go to let's go to a blank screen. Okay. Remember, this class is about big big data analytics. Okay, analytics. Now, again, the analytics part can be divided roughly into interactive visualization, right? And then more like statistical modeling, which I'm not going to cover very much because that's part of year 1 curriculum. And then sort of like machine learning. Okay. And then this here fork out into what? What are the two subset of machine learning paradigm that we cover? Come on. Unsupervised and supervised. Correct? Okay. Fine. Now, the data part, well, I did mention that big data is a whole host of technology platform and whole ecosystem. But the one thing about big data, there's 3V, right? Velocity, right? Volume velocity, which really is not something that we can cover within simulate within a class environment. Something that's going to be something that we need an actual platform with the data that you work with. Maybe if you work for large corporation, you have a Spark network, Spark server, and so forth. But this thing we can deal with. Yeah, we can deal with. Now, so far, this thing is quite annoying, and I have to keep turning this to the receptor, which is, I think, is that little guy there. I'm pretty sure. So I can have to move here. Okay. So in terms of variety, okay, I think fundamentally we talk about this kind of 4-number scale, right? 4-number scale, and you can think of it as two types of things: categorical data and numerical data, and then you have this what's it, nominal, ordinal, right, interval, and ratio. Okay, right? So the only thing that so far that you've been playing with, which is remotely big data or remotely of a variety, is to deal with categorical data. Okay, for example, label, like this is a cat, this is a dog, and so forth, right? But you haven't dealt with a lot of the input side. Okay, in other words, if I talk about the label, this is a cat, this is a dog. Okay, cat is 1, dog is 2, giraffe is 3. Okay, so it's not numeric, it's categorical data. It's more application oriented, but it's sort of like the output end. On the input side, you haven't dealt very much with it. For example, when I gave you example about identifying cats and dogs or male and female, the characteristic that allows you to make that prediction will be numerical still, like the weight, the height, or whatever, number of legs, okay? So it's still kind of numerical. But so on the input end, think about this kind of thing. Supervised learning, there's an input and output. We haven't really varied very much in terms of the input. Okay, so the input is kind of like a numerical table, right? And I think if I am not mistaken, all the project that you guys were talking about last class, everybody had some form of tables. Okay, so that means your input data basically fits on an Excel. Okay, it's a little bit like that. It's like a spreadsheet. So data item number 1, whole bunch of number. Data item number 2, whole bunch of number. Data item number 3, whole bunch of numbers. Okay, that's what you were dealing with. Okay, so now today, explore this a little bit, the variety bit. Okay, so instead of each data point being columns of number, okay, say 10 dimensions, so that's 10 different numbers. We're going to say, what kind of variety can this take on? Okay, so in a typical big data class, there's a big focus on a couple of things. Okay, so we have this thing where this is called a vector of numbers. So that's what we talked about. We can put that in the table. Okay, now what other variety of data can you get? Okay, well, right away you can think of what? Picture, right? Picture, right? Now, picture, we can devote an entire class on processing visual information. Okay, like have a picture screen. Okay, so picture, in a way, if you think about it, it is an array of numbers, right? In fact, there are 3 arrays of number. There's an array of number for red value, 1 for blue, and 1 for green. Okay, and if you talk about video, then you can say that there's 1 for every time slice. Okay, so that's one variety already. That's not traditional data. Okay, and again, once it's not traditional data, you can't do traditional statistics. You need to use machine learning. And that's why you have this neural network and so forth to do this. Okay, so that's one thing. One's picture. All right, fine. One is a sound. Okay, so you can think of this as audio, video. Okay, sound file. Okay, sound file. Okay, what else? Text. Okay, text. So this is also something that's not numerical. You cannot treat it through traditional statistical method. You have to do some kind of, and that's where you get this thing called natural language processing. Okay. Now, today is about what's called graph learning or graph data. Where does it fit in? Well, I'm going to say it fits in some kind of about here. Why do I say that? Because you will see that we're still going to deal with numbers. We're going to deal with numbers still, okay, as if we were dealing with Your height, your weight, that's a number, right? We still deal with number. Or, categorical data, 1 is equal to cat, 2 is equal to dog, 3 is equal to giraffe. We're still going to deal with that kind of number. But it's a structured kind of numbers. It's not just a list of numbers that you can put like this in. Okay, so that's the first thing. We are going to be dealing with numbers today, but the number that exists in some kind of topology or some kind of structure. Okay, so that's what you have to get ready for. So this is where graph. Okay, so that's my orientation. This is where we're heading at. Okay, we're going in this space right here. Okay, we won't cover very much this specialized area like sound or picture or audio video signal processing. That's sort of like a specialized area. But this turns out to be very general. Okay, and that's why I'm going to spend a lot of time. In fact, the entire class today is about graph data. Okay. Okay. So first thing first. Let's talk about location. I'm just going to talk about location. Okay. When I talk about location, everybody has an address, right? Right. So let's say we have this grid, this x coordinate, this y coordinate. I ask you, where are you? How do you give me an answer? You give me an answer of your address in terms of your coordinate relative to the x and y axis, right? So third row back, 3 columns to the right. Now I do something else. I ask you to reach out and hold your friend's hand, whoever you can hold, okay? Right? Now I take away the coordinate. You can no longer give me your address in terms of where you are on the XY coordinate. You can't, okay? Let's say once you start holding each other's hand, I flood this room and everybody's floating, okay? So your location no longer pinned down to coordinate anymore. Okay, how am I going to access individual person? How are you going to give me your address? Exactly. You are going to give me your connectivity. Okay, so this is first abstraction you're going to do with today. You are no longer tied to a coordinate. Okay, you are defined by your connectivity neighbor. Okay, my right, let's say you have just 2 hands, right? So you use right hand and left hand. So if I want to know where you are, your answer is not 3rd column, 2nd row. Your answer would be my right hand connects with this guy. My left hand connects with that guy. Okay? So how do I represent something like this as an object of, as a data? Graph. Okay, yes. Very good. It might be too good an answer, because most of the time when you walk in, most of the still when you walk in year 1, a graph is a plot. Okay? This is what you mean by a graph. Okay? From now on, as an educated person in data analytics, this will never ever be called a graph. Okay? This will be called a plot. This will be called a plot. It's not a graph. Now, okay, once you get that definition of graph, like graphing things on a piece of paper out, yes, your answer is correct. It is a graph. How is that a graph? A graph consists of, well, a graph is used exactly to represent what I was telling you about, where you are relative to who you hold your hand to. Okay, so a graph is a collection that's the first thing. Graph is defined by two things. V itself is a set. So this is a coupling of two sets. V is a set of things called vertices. This is a plural of vertex. Okay? Another word for vertex is arms. So, vertex. Okay? Yes. No. Okay. Now I'm going to draw a picture of a node. That's you. Who you are is a node. You are a vertex. Vertex one, vertex. Okay. Now everybody has right hand and the left hand. Okay. And the edges or arcs is like the arm. Okay, you don't need legs here. Yeah, legs here. You don't need legs. Right. So a graph is a collection of nodes or vertices. Each vertices have an edge or an arc that links it to the next vertex. So what is a common language word for graph? Network. Okay. So this is network. Now, when you are in real life, this is a signal that this is the application that requires this tool. So graph, you can think of it as graph as a mathematical representation of network. Okay? As long as you understand what network means. Okay. So in an application, now when I was sort of like working on this area 20 years ago, it was very difficult to convey the concept of empirical network, sort of like beyond, you know, who knows who. But now my life is much easier. Why? Because you guys live in the age of what? Social network, right? So social network is precisely the application of graph data. Let me say that again, okay? If you want to do analysis on network, any kind of network, in particular social network, the tools you need is the tools that's going to work with graph data. Okay? So, graph is not a plot. Graph is a mathematical object for representing real-life network. Okay? Why don't they just call it network? Well, because graph came earlier. As you saw from the video I sent you, the notion of graph is 300, 400 years ago. Okay, social network is only 50 at most. Okay, so graph came first from Euler, German mathematician in the video that I was alluding to. Okay, so let's see what it looks like. I could do this in colors, but anyway. So this is you. So this is an example of network. Okay, so obviously we have longer hands. Now, imagine that this guy's hand, okay, my left hand, the hand holds like this, but I can also have hands that go like this. So after a while, I'm not going to draw a person anymore. It's just too complicated. For example, okay? Right. Can you guys see now that this is actually a collection of how many objects? How many objects can you count in your head? How many? 5. Well, actually, you should count like this. This graph has vertex. The number of vertex is what? 1, 2, 3, 4, 5. So yeah, your answer is correct. But that's not complete. Your answer should be that the number of edges is 1, 2, 3, 4, 5, 6, 7. Okay? Right? Okay, good. Let me ask you a question. Just this is a sort of like a common sense. If you have n verse, how many distinct edges can you have between any two? Okay. Okay. If you have n, okay, that was distinct. How many? Well, I just and right? In person, each person can hold the other person's hand, so that's n minus 1. But I hold your hand and you hold my hand is the same thing, right? Because it's an edge. So I divide that by 2. Okay. So think of that, right? Think of that. If I have n vertex, I have uniquely, you know, how many connections can I have? Can there be? How many pairing can there be? Yeah. So that's obvious, right? If you have 3 persons, think about it. If I have 3 persons, okay, the first person can connect with what? They connect with the second person and the third person, right? Doesn't connect with himself. Okay, what's the second person is going to connect to? This person is going to connect to the first person and the third person. And the third person is going to connect to the first and the second. Right? So this is 3 times 3 minus 1, which is equal to 6. 1, 2, 3, 4, 5, 6. But because 3 and 1 and 1 and 3 is the same thing, divided by 2. Right? Okay. So when I did this, anybody wants to guess where I'm heading at? I want to store this picture on an Excel, on a spreadsheet, yeah, because it's very convenient. Yeah. How would I do that? Well, I'll do exactly this. Right? So now, what I'm going to do is create a table. And simply put in 1 when there's a connection. When there's no connection, there's no 1. So what is completely connected? It's going to be 1. Correct? Right? This is my connectivity, right? It happens that this one and that one is the same. So you have actually 3 unique. Okay, you actually have 6 connectivity defined. Yeah, which gets you to do another thing. What if this relationship is not mutual? Can you guys think of a relationship that's not mutual? Well, in this class, if you know him, he knows you. That's mutual. But if I'm talking about larger population, you probably know a famous actor or actress. Chances are that famous actor or actress has no idea who you are. Right? In that case, it doesn't have to be symmetric. So you can have something like this. Right? 1 does not know 2, but 2 knows 1. Okay? But either way, would you agree that this has as much information as the picture? Okay, you have to buy this first. Otherwise, we can't go on. For example, when we were counting the number of edge, right now, you said 5, right? What were you counting? The number of row or the number of column. It's a square. It's a rectangle. It's a square. It's not a rectangle. It's a square. So how many vertex do you have? Vertices? 1, 2, 3. How many edges do you have? Again, you can count in a symmetric way, like, divide by 2 or not. Let's say you don't divide. Let's say this is directional. Okay. 1, 2, 3, 4, 5. Now, let me make it more concrete. Look at this one. Look at this in particular. Let's say 1, 2, and 3. And let's say this is, just now I went from picture to table. I'm going back from table to picture. Except this time, I'm going to make life a little bit more difficult by saying that now it's asymmetric. In other words, relationship is one way. You can know a famous actor doesn't know you. Okay? So let's call no. 1 knows 3. 1 knows 3. Now, because it's no longer symmetric, okay, I have to add another symbol just to make sure in which direction am I pointing. Okay, so it's no longer like a row tying 2 persons together. It's more like an arrow. Okay, so this one here is this arrow. Okay, 2 knows 1 and nobody else. 3 knows 1 and 2. Okay, so right away, by adding direction, okay, it's more general, right? It's more applicable. So you can say in some situation, A knows B means the same thing as B knows A. But in a lot of situations, it doesn't. Okay, a lot of situations, it doesn't. In real life application, a lot of time, this represents some kind of information flow. Yeah. So the direction of flow really matters. So would you agree, okay, that this graph, 1, 2, 3, this is my vertices, right? And what's my edges? These guys, okay? How do I store it? How do I store it? I can store it as a picture, but I can store it here as a table, okay? Except this is not the table that you were used to. In the table that you were used to, this is a person. This is a height, weight, is whatever, it's a vector, right? So this is the dimension that measures the attribute of this guy. Okay, whereas this table, you will always have the same number of row as number of column. Okay, because it's about connecting n people to n people. Okay, so it's always a square What's the word I'm going for next? Matrix. Okay, so right away, just as when you do linear regression, the fundamental object is a vector. You are a vector. Okay, x1 is height, x2 is weight, x3 is age, say. Okay, so vector of dimension 3. Okay, and you also are a vector. Everybody's this is sort of data model we had. Now you don't. Now the dimension is defined by the number of entities, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's a 10 by 10 matrix of connection, pairwise connection. Okay, pairwise connection. Now, you are going to ask, if you are, ahead of it, you're going to ask me, wait a minute, I have one person, there's a whole bunch of people, and my analysis here is going to be limited to pairwise knowledge. What about groups? Doesn't it matter? Yeah, you can have groups, right? You can have association, you can have hierarchy. That will come. But the beginning of the data set is a matrix. It's only pairwise. In other words, I'm going to represent graph and graph is equal to collection of V and E. But what's V? What's V, guys? V is individual vertex, right? So let's say I have V1, Vn, right? 1, 2, 3, 4, 5, 6, 7, N. Okay, what's edge? Edge is going to be number A, I, J, I going from 1 to N, J going from 1 to N. And that number can be what? Two numbers, 0 or 1. Okay, so if you understand this, you are pretty much understanding what graph is all about. Okay, you haven't done any analysis on it. You can't. That's what this I'm going to teach you. But first, understand that this is what we're dealing with. Okay, this is unlike anything you've seen because you used to see what? A number. You used to see a number. A number is a scalar. You used to see a whole bunch of number. That's a vector. In that context, what's a matrix? Matrix is a thing that multiplies your vector and gives you another vector. So that matrix performs a function, right? In this case, this matrix is the thing in itself. Very different, right? It's very different. Okay. When you study linear algebra, a matrix multiplies by a vector, gives you another vector. It performs a job. It does a job. It does a job. It's not data. In this case, matrix is data. Okay? In matrix is data. And if you think about it, linear regression inputs a vector, right? Inputs a vector, and you can do, coefficient. Well, coefficient multiplication, essentially, that's matrix algebra, multiplying dot product or matrix by a vector. See, so it's doing something in that context. That matrix is doing something. It's doing the multiplication. It's giving the transformation from X to Y. In this case, the matrix is not doing anything. It's just data itself. So this is the matrix representation of a graph. Because this matrix has a specific job to represent the graph. In particular, it represents who is holding whose hand. The technical word for holding whose hand is adjacent. You are You can hold his hand because you are adjacent to him. Otherwise, your arms are that long. So this matrix is given a special name. It's called, sure enough, okay? See, that's why I use the word A, right? You could use E for edge, but not. Yeah. Use A for adjacency. Use A for adjacency. So, how can we make this more realistic? How can we make this more realistic? First of all, I already made one thing more realistic by saying it's symmetric. So IJ is not the same thing as JI, right? You know, a famous actress had no idea who you are. Okay. So that's allowing more realism. How else can you add realism? Let's say this is a network of friends on Facebook. Are you equally friendly with everybody on your network? No, you're not, right? So what if instead of 0 and 1, I give it like a percentage number? If you are perfect buddy, it's 1. If you don't know a person, it's 0. But what if you just barely know a person? Instead of making it 0 or 1, let's give it a number in between, right? So now there's another word called weighted adjacency matrix. Instead of this, I would write Wij belongs to, now it's an interval, 0 to 1, right? This is 0 or 1. You know the person, you don't know the person. This one, you know the person intimately, like he's your twin, that's 1. The other person, you don't know at all, 0. If you barely know a person, maybe it's 0.1. Yeah, so that's one way of adding realism. What else can you do? What if instead of, well, what's the opposite of friends? How about enemies, right? So you can think of positive and negativeness. So this can have from -1 to +1. Okay. Now in real life, we are adults here, we don't have enemies. But in a sense, if everything you do is the exact opposite of the other person, you can think of that as being like an arch enemy. Okay. Whenever I want to go right, this guy will go left. Okay. So that person will have a negative association with you. Go back to your statistic 101. What is a good measure of that? Correlation, right? So I can actually use correlation matrix to represent how well the person goes together. Okay. So now it's not Aij. Aij is equal to 1 means I knows J. It's Wij equal to +0.5, meaning I and J have a correlation, positive correlation, not perfect. What if A, now I shouldn't use A, I should use W. Wij is equal to -0.7. And that -0.7 is a negative movement. So that means whenever A goes up, I goes up, J goes down most of the time. Where do you see this? Financial market, right? Instead of having 10 people, you have in the stock exchange of Thailand, there are 400 listed stocks. Every single pair of them has a correlation between them. So there, instead of W, I could have used. What's the symbol for correlation, guys? Rho, right? Rho at J. Okay. Now, just did a paper for capital market research development fund that used some other measure, not correlation. But that's a bit advanced, COBRA. But here you see the data set. Okay, so graph data is basically a matrix. Okay, and this matrix can have, if you look at it, you can see right away what are the properties, right? You can see that it's either 0 or 1. So that's sort of like binary, yes, no, unweighted. You can have something that's weighted. You can have something that's weighted and signed. In other words, positive as well as negative, right? Right. Yeah. Okay. So that's graph data. Okay. That's graph data. Now, what else can you do? Make life more realistic. You can have multiple type of relationship. So for example, I can have IJ, by the way, this could be a number that doesn't have to be a weight, right? It could be, for example, number of years you know each other. In which case the minimum is 0, the maximum is, I don't know, 50 years. Okay? So it doesn't have to have a limit to 1 necessarily. It can be anything. The point is it is a square matrix. So what's graph data? It's a square matrix. Now, if you have more than one relationship, one matrix could correspond to number of years you know. Another is number of years you have been in the same class, right? So you can have more than one matrix. Now, technically, that's a tensor, but we'll leave it to other days. So that's it. That's graph data. Okay. Now, by the way, before I go on, let me just show you why graph data is not something that you can easily store in Excel. You could, but you guys work with Excel, right? Are there more rows or there are more columns? More rows than columns. Okay. Basically, Excel looks like this. Yeah. Why did they? This is the limit of Excel. In every generation, maybe it gets bigger, but it's always this kind of shape. Why did it's drawn this way? Because, well, if you think about it, this is data sample number 1, number 2, 3, 4, 5, and this is maybe height, weight. So this is the dimension of the measurement, right? The measurement dimension is usually restricted. It's not 1,000. Okay, you just take this many measurement of a person, but you can have a hell of a lot of a person. So it's always like this. It's always like this, right? So that's why if you look at, the limit of the Excel page, it's going to look longer this way than that way. It work for data set, graph data. Actually, it's opposite. Because if you have n data, n person, what do you need over here? Right? Okay, so this is why now database, now this is something that you need, it's a little bit about big data platform. Database is built around this kind of model. We have this relation database. It's kind of built along tables. Okay, you can think of traditional database, SQL, whatever, as a model after tables. But what if the fundamental object is actually a square matrix? Okay, then that kind of traditional database would not work. On a big scale, you need things like a graph database. Okay, but we won't worry about it. We'll deal with small data. So you can still put in the Excel. Okay. Right. So industrial strength matrix cannot be stored on Excel doesn't work. But for a non-industrial strength or smaller problem, you certainly can. Yeah. Before I go on, is n times n minus 1 divided by 2 a big number? It is a big number because it's n squared essentially. It's essentially n squared. Now, think about not 10 people, 1 million. Okay? How would you store that data? Well, it's going to be 1 million times 1 million, right? But if you think about it, do million people know million people? No. Most of the time, it will be zeros. So, as a hint, okay, this is not a database class. Yep, sorry. Exactly. You're right. That's exactly how it's done. You keep a sparse matrix. The word sparse means that of all the 1 million times million minus 1 divided by 2, you only have certain items that are 1. The rest is 0. So you just keep the 1. Okay? In fact, the database looks like this. For example, if the second person knows the fifth person, this is what you store. That's it. That's all you store. Okay? So if the second person doesn't know anybody else, you don't have to keep 1 million more number. You just keep this. Okay? And whatever. So it's a database, a sparse. This is called sparse array. Array is the same thing as a matrix, except this. You can use the word a sparse matrix, but the proper word is sparse array because you're no longer storing it as a matrix. Yeah, but it represents the same thing. Okay, so think of a big million by million database of who knows whom in a population. Most of the time, people don't know each other. Okay, maybe you know 10. Okay. So certainly 1 million, 10 person each, 1 million times 10 is 10 million. It's not 1 million times 1 million. It's not million squared. Okay. So this is why it's usually stored as a sparse array, not in an Excel. Okay. So now let's work with them. Okay. So far we know what the data is, right? Let's do analytics. Now you guys go to the line. ก๊อฟช่วยดูนะว่าทุกคนทำได้นะเดินไปเดินมา You guys log in line, right? Just copy that command. Okay, in the notebook. So for example, now you can work with any data set. Okay, I just happen to choose this one because I think it demonstrates all the concepts that I want to show. So this is from example data. In fact, you guys remember that if you go to example data. Huh? Oh, yeah. Exit. Oh, yeah. Okay, just key in exactly as I do, right? I'll make it bigger. So you see that example data, right, has all these different groups. Now, what I'm going to focus on is certainly this. Yeah. So network refers to application, graph refers to mathematics. So, network graph. So let's say if I did this, I copy network graph. There's a whole bunch of them. Network graph. See, there's a whole bunch of them. The one that I picked out for this class, I think is L. So jazz musician, okay, somebody was doing network of jazz. I'm doing this one. This is a musical, okay? It just has a nice number in there, okay? So that's why I chose this. So example data, Les Miserables graph, it's I can come back, explain later what all this means. But the point is now I have, okay, shift enter. I have a 77 by 77 matrix. Okay, you guys want to see what it looks like? Yeah, we can certainly see what it looks like. Yeah, let's make it a matrix form. See? Right? Now, first of all, you guys remember? Well, you have to read from the description. Yeah, but I already read the description. What this means is that there are 77 characters in Les Miserables. Okay? Like like musical play has 77 characters. Okay? Not all characters are going to appear together, except when they take their plot, right? So this one means character number 1, I, and number J appear in the same scene at some point in the musical. Okay? So ignoring the diagonal, because you don't need to say I appear with myself. After character number 1 appears with character number 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7, 8, 9. Okay. Likewise, character 2, 3, 4, 7, 8, 9 appears with character 1 because this is symmetry. Okay. So notice right away, say, are there any numbers that 0, 1? There isn't. So this is a binary connectivity, Boolean, yes, no. You either pick the same state or not. It doesn't say anything about how long the scene is or did they talk to each other. It just records that throughout the entire musical, 2, 3, 4, 3 hours. I think maybe sometimes I don't remember. Let's say in 3 hours, 77 characters appear, and this is the pairing that they appear together. Okay, it doesn't mean that all 9 of all of these appear at once, right? Because 1 can appear with 2, and then with 3 in another scene. See what I mean? So this means at some point, this character appears with that character. That's what it means. Okay, it's 0, 1. It is symmetric. Okay, it's a little bit like small network. Yeah. So get rid of that. Right. Now, there's some. Normally, when you work with example data, you have different properties. So, for example, you have property. Okay. Now, if I want to say how many vertex count, okay? Vertex count. That means 77, right? Like I said, what's a vertex? Vertex is you, right? How many vertices are there? 77 characters. How about edge? How many edge? 254. Okay, 254. Okay. Out of how many possibility? Well, that's certainly 77 times 76 divided by 2, right? Yeah. So anyway. You don't need this. This is not that important. Now, because the matrix is so big, right? One of the easiest way, and in Python, you have to do matplotlib, which is going to take like a long time. But in this case, just use what's called list density plot. Okay, list density plot. That means when the points are dense, it has a different colors than when it's not dense. Now, normally it's going to have interpolation, meaning that it's trying to smooth out. If I put in interpolation of 0, that means it doesn't smooth anything out. And this is what I get. Okay. Now, how do you interpret it? Okay. Now, the matrix go from 1 to 77, 1 to 77, right? But in this case, 1 is at the bottom. See that? See that? The first person appear in the same scene as the second character, third, fourth, fifth, sixth, seventh, eighth, ninth. Okay, so this is kind of, you know, flip it like this, you get 0 and 1. So blue or dark color is 0. Yellow or light color is 1. This is much easier to visualize than a whole bunch of 0 and 1, right? For one thing, you can look back. Let's say I never told you anything about what this data set means. You can tell right away that this is symmetric, right? Symmetrics, right? And because you don't have white everywhere, it's fairly sparse. Now, there's technical definition, like you can say, well, if it appears in 10% of the slots, then it's sparse. If it's more than that, it's not sparse. But this will probably be treated as a sparse, okay? It's not one of those things where a lot of actresses appear on stage and sing together, so it's more like an intimate kind of play. Right. Now, here's an interesting thing. This is a matrix. It's not a graph. It's a matrix that represents a graph. So how do I turn it into a graph? Okay, I can show you example later in Python. We use what's called Network X library. And that's the one that I will show you later, but it takes a few steps. In this case, we just use one step method. Connectivity graph of lemmas is adjacency graph. That's it. Okay, see what happened. So I get the matrix, I turn it into graph. Now, this graph, just a whole bunch of numbers. Okay, you can't see one, but I'm gonna give you a little hint. You guys remember that after character number 1 appears with 2, 3, 4, 5, 6, 7, 8, 9. Well, okay, I'll show you the label and the number will come up. But right away you can sort of see. So this, if you count the number of circle, number of nodes or vertices, how many do you get? 77. How many lines connecting them? 254. Right? So, by the way, in mathematics, it's very easy, it's symmetric. If you start with a matrix, you put command called adjacency graph, it converts matrix into graph. If you start with a graph and you apply command adjacency matrix, it turns graph into matrix. Okay. So if I have this graph, yeah, and I turn it into matrix. How do I do that? Adjacency matrix. Is it the same thing as this? True, same thing, right? Just go back and forth. So you do this forever. And important part is you don't have to initialize node. In network X, you have to initialize, populate, and all kind of stuff. But this one, just one step. Now, I want to show you a few more properties. Okay, so I could actually try to find an example. Instead, I just make up new example. Okay, in this case, I'm going to make 3 more examples. Okay, this is random. Number 1, it's a random graph with the same number of this guy, of this data. So this is actually 77. Okay, but I just put it. So it's the length of this matrix. So that's the number of rows. So that's 77. Okay, I'm going to make random graph of 77 vertices. I'm going to make 3 of them. Now, this is my condition. This is random, meaning, connectivity is random. And the number of edges is equal to total flattened matrix. When you flatten the matrix, it just becomes a string of number. You add them all up, what do you get? 254, right? This is 254. Okay, so it's going to have the same number of edges as the data, but it's going to be right. Okay. Now I create another one. So this is going to be 254, right? How about this? How about I take the length, which is 77, right? Multiply by 2, that's 154. So instead of having 254, just have 154. Instead of 154, have to 77. So it's sort of like random and less and less. Now, the example I want to demonstrate is not only random, it's also directed edges. What it means is that not symmetric. It's not 1, 1, it's 1, but maybe this is 0. Yeah. So I just make this up. Okay. So you can, on your thing, you can just say random graph. Okay. And then how many? 77. And how many edges? 254. You can do this, okay? If you don't want to type in the long line. Yeah, let's do that. Oops. Yeah. Now, this one, by default, is not directed edge. So if I want a directed edges, is true. Okay, so now you can see that it has arrowheads. See that? There's a difference between just now and if I have false or default, it's going to have just a row linking. Okay, so that's what I made up. So I created this up. I made this up. Okay. Notice what happened. The first one is very jumbly. Okay, it has the same number of nodes, or vertices. It also has the same number of edges. Second one has less. Third one has even less. But guess what happened? Look what happened. This one seems fully connected, meaning somehow you can get from one person to the next person one at a time. That's what it means by connected. Remember DB scan? It's a little bit like that, right? Remember that? Yeah. Well, here you can still get everyone. But here, because the connection is so few, you start forming islands. You can't get from here to here. You can't see what I mean? It's a little bit isolated, right? So this becomes unconnected component. And that's why I wanted to create this example, because in the first example, because it's a play, right? I mean, characters have to appear together, and you would never see a play where 2 characters appear together and not with anybody else. It's quite rare to have that kind of play. So chances are everybody's connected at some point. Okay, everybody appears with somebody. But here, this is one of those weird plays where, look, not so many people appear together. So maybe these 2 characters appear together, these 2 appear together. This guy is a soliloquy. You know what soliloquy is, right? When a guy comes up and speaks by himself, right? So this is a little island. Can you guys count how many islands? So there's a big island. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So this you can visualize. Well, obviously it's visualized, right? The whole point of data analytics is you can analyze this pattern when you have ability, right? You just use mathematics to analyze for you, because you can't just visualize it, you know. Yeah. So how many networks have I got now? I've got 77 here, representing characters from a play, from a musical. This is a random connection. So, you know, it's kind of evenly distributed. There's no feature anywhere. Everybody seems to be huddled together. So this is a bit like that, but just less connectivities, but still kind of like, you know, random. This is random, but it's so sparse that you end up with singlets. Yeah. What does this mean, by the way? This means that this item doesn't have any connectivity. It's all zero. All zero. Okay. Okay. So likewise, this is a graph form. I'm going to turn to matrix form. Okay. Aha. Look how cool this is. See? Instead of having a whole bunch of numbers, the algorithm determines that there aren't that many non-zero. So let's keep it like this, called sparse array automatically. Okay. Now, if for some reason you don't like sparse array, you want to keep it zero, you can force it. Okay, but that's not efficient. So automatically, whenever you have a matrix that has a whole bunch of zero, you want to keep it as a matrix. By default, it will go to sparse array. Yeah. If you want to turn back to normal form, you use the word normal. So you can have something like normal apply to this guy. Let's take the first one. See, becomes normal. This is wasteful. This is very wasteful. Yeah. So this is normal form of this. But the thing itself is kept as a sparse array. Now, you recall that whenever there's a plus, you usually are able to click and then get information. Well, here it is. So just say that, remember that? It doesn't keep all the zeros, it only keeps the one. And not only does it keep one, it gives you the density. So it's only about 8% filled. Yeah? Does that make sense? Why is it 8% filled? What do you think that is? What do you think that is? Well, you can do this, right? Let's flatten this. And then let's take the total. 500 edges. Divide by length of this guy square. And make it numerical. There it is, 8%. See? So this 8, 5, 7 density, it's the number of edges, number of ones, divided by 77 square. So it makes sense. Now, obviously, you can do this calculation, so it's not a big deal, but it's given for you. Okay, so now we have this guy. Yeah. So let's go back, review a little bit. Let me review what we did, and then we'll go for it. First, you guys are familiar with situation where each data point has a bunch of numbers. And that numbers can be height and weight. And you can say height is an x-axis, weight is the y-axis. So where are you? Well, you read out the number. That's the coordinate. Now, I don't care about coordinate. I care about relationship between points. So I ask each point to hold each other's hand. And I say, whose hand are you holding? Whose hand are you holding? Okay. In this case, in human being, you'll have two arms. But in my data set, you can have as many hands as you like, right? How do I represent that? I can represent it as a graph. Mathematically, it's collection of vertices, V, collection of E, edges. How do I draw it? I draw it with a bunch of nodes and line between them. But how do I store it as a data? The neatest way to do it is to store it as a square matrix. Okay? And so this thing here, all you saw was that I can go back and forth between the matrix, apply adjacency graph to it, turns into a graph. I can see it. Or I can take a graph, apply adjacency matrix function to it, turns into matrix. Right? Except this is a bit more clever. The matrix is technically rows 77 times 77 matrix of zeros and one, but that's wasteful. So instead of keeping it as a full matrix 77 by 77, it just keeps the one and keep track of where the ones are. And that's called sparse array. Okay, so far, all I'm doing is to say, situation, real life, we want to model relationship. The relationship is the data, is the matrix. The matrix's job is not to multiply to another vector and give you another vector. Okay, the matrix is the data. Okay, but you haven't done anything with it. Okay, so far you only constructed the matrix and the graph. Construct the graph from the matrix, keep the matrix, record the graph. Okay, go to a break for say 5 minutes, come back and say, what can we do? How can we analyze the graph?